Section 11.1, Basic Notions, is where we're going to begin today. And we're going to start by giving some definitions, or maybe even some of them aren't exactly definitions, but they're sort of descriptions, at least a little bit, of what we mean by certain things. For example, the word point indicates a location or a place. Some geometry classes will even say this is an undefined term, and they will give you no definition. A point is a point. And you have in your mind what we mean by that. You do need to be careful to notice that it does not indicate size. So you can't make a big point or a little point. A point actually has no size at all. It is denoted by an uppercase letter. So we'll use capitals to designate points. We also have lines. The word line is used incorrectly all the time. A line indicates length, and it indicates infinite length. It goes on forever in both directions. It does not have any width, so there's not a thick line and a thin line in terms of geometry. A line is a line. And also hear students sometimes say straight line. All lines are straight. Okay, so straight doesn't actually give any more information than the word line did to begin with. If you're given 2 points, A and B, there's exactly one line through these 2 points. And I can't remember if I write it down later, so I'll write it here just in case. We would write line AB with the 2 capital letters. There'd be a bar on top with arrows on both ends. That's line AB. Sometimes lines will not be denoted by the two of the points that they go through. They'll actually be denoted by a lowercase letter. I use the example, this lowercase k, instead. There's 2 ways we could denote lines, the lowercase letter or the 2 of the points that are on the line. A lot of times people will say line when they mean line segment. A line segment is a piece of the line that has 2 endpoints, and it includes all of the points in between. So a lot of people will draw something like this and call it a line. It's not a line, it's a line segment. It has a start and it has a stop. If it didn't have a start and a stop, it would have arrows on the ends, and then that would be a line. Okay, so this is a line segment. Now, a ray, sometimes also called a half line, is a subset that has one end point, but then it extends the other direction forever. So it looks something like this. A starting point, or an end point, and then the arrow goes infinitely in the other direction. And it doesn't have to be that way. I mean, it could have been like that, right? I mean, the arrow could point the other way. It doesn't matter which direction the arrow points. Collinear points. 2 points are always collinear because there's always a line between every 2 points. So we don't talk about points being collinear if we're only talking about 2. If you have at least 3 points, then we can talk about collinear and it actually has meaning. Collinear points are 3 or more points that are on the same line. If A, B, and C are collinear, so they're on the same line, we say that B is between A and C if AB plus BC equals AC. Okay, so you might notice that I used the AB, the BC, the AC, and there's no lines or line segments, or there's nothing on top of them, right? Did you guys notice that? That's on purpose. It's not just like I forgot. If there's no line or line segment notation on top of them, it actually represents how long it is. It's the distance. So when we see AB like this, this actually means the distance or the length of that segment. So the distance from A to B, the distance from B to C, or the distance from A to C. And this sort of argument, of course, you recognize as truth because you've seen it before, dozens of times. If you have these 3 points, and they are A and B and C, clearly, if I take the distance from A to B and I add that to the distance from B to C, I have the distance from A to C, right? And that's always true if they're collinear. If they're not collinear, for example, let's say this didn't look like this and it looked like that, this fact would not be true because the distance from A to B added to the distance from A to C is not from B to C is not the distance from A to C, right? There's a different distance. The most direct distance is actually not the same. So this fact only works if you're talking about collinear points. Intersecting lines are lines with exactly one point in common. Lines don't have to intersect, but they could. And if they do, they're only going to cross once. Concurrent lines are lines that are 3 or more lines that all intersect at the same point. So if you're taking a look at these diagrams below, we would say that this, we'll look at the left diagram, that line AB and line AC intersect at point A. But these 3 lines are not concurrent because they don't all intersect at the same point. Now if you look at the second diagram, this point D is a place where there are 3 intersecting lines all at point D. So these 3 lines, which would be DG, DF, and DE, would be concurrent lines because they all intersect at point D. All right, so we're going to move a little bit out of our 2-dimensional that we've been talking about into 3 dimensions. A plane indicates a surface, not a thickness. If you are given 3 non-collinear points, okay, 3 points that don't all lie on the same line, then there is exactly one plane that contains all of the points. We name planes by those 3 points in the plane, or any 3 points in the plane, or by a Greek letter such as alpha, beta, or gamma. So this is alpha, beta. Oh, does anybody remember how to do gamma? Okay, I'm not going to write it down then because I'm not 100% sure. I haven't written one. It's gamma in a while. I do theta, but I didn't write theta down. They're a Greek letter. So if we use a Greek letter, we're talking about a plane. Now, I want to talk a little bit about this classroom because it's easier to visualize if we talk about sort of the corners of our classroom creating planes. So if we were to imagine the point in the corner up here on the top right, okay, where the ceiling and the walls cross, that point, the point in the bottom corner over here, and the point in the top corner at the back of the room, they all create, they're non-collinear, right? There's not a line that contains all 3 of them. But they do all lie in the same plane. The plane would be that wall. That wall would represent, without the thickness of it, of course, but the wall would represent the plane in which all 3 of those points lie. And it even works if you don't talk about one wall or one floor. For example, we'll use the 2 corners up here, right on my far right and our far left, and we'll use, tell me your name. Rachel as our her third point. We'll use Rachel's desk, okay? So if you're thinking, got to be a point on your desk, or this doesn't make any sense, but work with me here with the image for a moment. And you might be saying, well, okay, but like those lie on a couple of different, they lie on the ceiling, they lie on the wall behind me, but her desk doesn't. That's okay. If you were to tilt a plane so that it intersects that line that contains them both, and it also comes down at an angle and intersects the desk, that would be the plane we're talking about. So in the sense of how we think about it, we would think about it being a diagonal kind of plane, right? And that's the plane we would have for those 3 points. All right, coplanar points would be points that are in the same plane, just like collinear points are points that are on the same line. So obviously 3 points are always coplanar. So it doesn't even make sense to sort of describe them that way. They have to be. So really, to talk about coplanar points, we're talking about at least 4 points for it to make sense. Okay? And then non-coplanar points would be points that cannot lie in the same plane. So if I were to use the 2 on the corner that I talked about before, right? The one on the bottom, those would all be coplanar to the back wall, correct? But then if I threw in the point in that top corner over there, I would be out of luck. There isn't a plane that contains that corner, these top 2 corners, and the bottom one on the floor. It just doesn't happen. So those would be non-coplanar points. We also have coplanar lines, and those would be lines that lie in the same plane. Again, sometimes that happens, and they do lie in the same plane. Sometimes they don't. If they intersect, they always do. right? If you have intersecting lines, they're for sure going to lie in the same plane. But not all lines intersect in 3 dimensions, right? They don't. So if we looked at this sort of line that is this top wall over here, goes from the front to the back, and we looked at the line that's this front wall on the ceiling, those would be coplanar because they intersect in that corner. The plane that they would lie in is the ceiling. But if we looked at, say, again, this line on the bottom or the top over here, and we looked at the floor behind me, those two lines are not going to be able to be drawn in the same plane. It's not necessarily because they intersect, but that certainly creates part of the question. If you were to take this line again atop the corner, this wall over here, and you do the wall over here, those two lines are not going to intersect, agreed? But they are in the same plane. What plane are they in? The ceiling, the one that's sort of represented by our ceiling. They're actually parallel, correct? So parallel lines would also lie in the same plane, and we'll see more options of those kinds of things later. Skew lines. Skew lines is that option. There are two lines that are not coplanar, and they also then naturally can't intersect and they can't be parallel. So the example I gave of this particular corner wall, issue up here, and my line along the floor over here would be skew lines. They're two lines that are drawn in space that do not intersect and they are not parallel. Okay, I just wrote those down in there. That's fine. And then two coplanar lines are parallel if they do not intersect. So I kind of already said that, but now it's written in sort of black and white. Coplanar, and they're parallel if they don't intersect. So the only way you get coplanar lines is if they are parallel or if they intersect, and if they do neither, then they're skew. All right, we desperately need an example because I've just given you like tons and tons and tons of language, right? All right, so let's talk about a couple of these. Can skew lines have a point in common? Why or why not? You said no.
Because they don't intersect, so they can't have a point.
No, you're right, because if they had a point in common, they would intersect, or they would be intersecting, if you want to get the English a little bit better. Hence, therefore, because we all now know coplanar. Intersecting lines are coplanar. So if they had a point in common, they'd be intersecting. If they were intersecting, they'd be coplanar. So yeah, that doesn't work. All right, our definition for being skew is that they're not coplanar. Can skew lines be parallel? No, they can't. And again, it's because parallel lines are coplanar. All right, we'll do one more example. Example 3. If two lines are in a plane, then the line containing them is where? Sorry, I didn't read that right. Let me try that one more time. If 2 points are in a plane, the line containing them is where? Where would it be located? In the same plane. Yeah. So in that plane, or in the same plane. All right, you don't go out of the plane to connect to those 2 points. A line and a point not on that line determine what? So it might help to sort of get in your mind a picture of what they're describing. You have a line, so let's just use the one behind me on the floor, that line, and a point not on that line. So pick another point somewhere in the classroom. What do they determine? What do they create or make if we were to connect them all? A plane, right? That's the image that we had when I used a line and I used your desk, right? We created a plane. So these determine a plane. Two different parallel lines. Think my sides of my classroom. If we were to somehow connect them, what will they determine? What will they create? A plane. Do you see a pattern? Okay, just checking. Yeah, this is a plane as well. They would determine a plane. And two intersecting lines determine what? A plane. So a plane can sort of be created in a number of different ways. It can be created by two parallel lines, two intersecting lines, a line and a point not on the line. They all create a plane.